What's an example of radiation that cools things?
Radiation that cools things doesn't happen, right? It's got to heat something up, right?
But
Emits.
Because the energy is flowing from the source to something else, right?
okay.
Right? Because heat travels from hot to cold, right?
Uh-huh.
Right?
Yeah, but there are examples of the other two that cool things.
Okay. Conduction is what? What's the difference between conduction and convection?
That's why I'm asking what's the definition of convection.
What's the difference?
Convection
gas
is
and
like,
solid.
yeah.
Okay, you have to have a solid here, right? Conduction is from solid to solid, right? So if you have a heat source, somewhere over here you have a heat source and you have, okay, so this is your, I don't know, stove or whatever it is you have at house. And this is the outside air, right? This is the outside air and you have double pane glasses, right? Right? Or
Yeah, sure.
does anybody know what the difference between a single pane and double pane glass is, right?
Yeah.
You can look and you can see, if you look over here, you can see whether it's a double pane or not, right? You can actually tell. So double pane means what? That much more insulation, right? So it makes it harder for the heat to escape outside, right? Or for that matter, for the cold to come inside, right? Okay? So that's conduction, when you're transferring heat through a solid. Convection is what? What is the example that they gave us? What example did they say?
On a hot summer day, when you sit in front of a fan to cool it down.
Okay, all right, yeah. So it's something blowing on it, right? So you're actually forcing air onto it. Okay, anybody have a different example?
I was just gonna say like wind, but that's basically the same.
That's natural, so that's true. Isn't
What else?
Like, you know those baths that they use to melt chocolate?
Fondue?
No. They have like water baths,
Uh-huh.
specific things that are made for melting chocolate that circulate the water and heat it up.
Okay, so that would be conduction or convection or radiation.
Convection because it's a liquid.
No, the liquid has to go.
Exactly.
Okay, so let's say, raise your hand if you've looked inside a computer before. Okay, has anybody built a computer before? Henry's built a computer before. Okay, so you built a computer before. Okay, so on the
it? Can't relate.
CPU, what do you attach?
You put something to cool it. I put a fan.
Oh, I guess it doesn't over.
Okay, so you put a fan on top of what? So in other words, there's a CPU here, right? The CPU is a flat.
Right, and there's the steel thing on top of that.
Oh, the heat sink. We have a heat sink here, right?
Yeah.
Heat sink that looks like this.
Yeah,
There's a bunch of fins, right?
yeah.
Right? So that it can get rid of the heat, right? Because the heat would go from here
Crap.
to the heat sink.
Yeah.
That would be what? Would that be this? No.
Isn't that conduction?
It would be conduction, right? Because you're going solid to solid, right? That would be conduction, right? But then it kind of radiates out if you didn't put anything there, right? It would just radiate out, right? And that would be radiation. Okay, but what you do is you actually clamp on top of here. What do you clamp?
A little fan.
A fan. We call it a CPU fan, right? A CPU fan that actually sucks air in and it blows it through.
Oh, I see. So it's all three, huh?
So that would be convection.
Is it water cooled?
Wow, too complicated.
Is it water cooled CPU convection? Because it's the water that goes to the heat.
What is
sink.
what is the definition of conduction?
But the water cools the heat sink, and then the heat sink cools the CPU. So is it convection or conduction? Because there's
Okay,
water.
so let's read what it says. Conduction refers to the mode of heat transfer that occurs when a temperature difference exists in a medium. Okay, the energy is transported within the medium from region to more energetic molecules to the region of less molecules. So conduction would be from here through to here, right? Okay.
Yeah.
So if this was water, Okay, so the question is whether it's gas or solid or liquid, correct?
Yeah.
Right? Isn't that what the question is here? Okay, so let's look at convection. What does convection say?
Literally a picture of the CPU.
Heat transfer occurs when a fluid, a gas, or a liquid in motion comes in contact with the solid surface, and it removes the free heat, right? So that if you had liquid here, it would be convection.
Okay.
So it's the same thing like in a nuclear reactor, right? When you have the nuclear fission occur, right? You send water through, the water gets heated up, so it takes the heat away from that source, right? And so that would be
If I bought you all the right parts, could you build a nuclear reactor?
no. Don't even go there. So,
It's a legitimate question.
Class
Huh?
project.
It's a legitimate
last
question.
project. Make a
Nuclear project for building a nuclear
make
reactor.
a nuclear reactor.
Wow.
Okay, so that's the difference between conduction and convection. Okay, what is radiation? Radiation is kind of all by itself, right? What does it say?
Or radiation.
Higher the temperature of the surface of the object, the more thermal. Okay. Yeah, so it's basically like you have a heat source like a stove, and it's heating the middle of the room, right? Just blasts heat out, right? Okay? You're not forcing the air around, so it's not convection. Okay, it's not conduction because it's not within the same material, right? It's just radiating heat out. Okay? All right? So that's the difference between these three. Okay? So let's go ahead and now look at conduction. Let's look at conduction. We're going to look at conduction first. So the plan of attack is this. I am going to talk today, the first half we're going to talk about conduction. Second half we're going to talk about convection. Okay? And then I'm going to give you a bunch of homework, which is way too much for you to handle today. So we'll take not Monday, Tuesday, right? We're supposed to be Tuesday, I guess, right? So Tuesday we'll take a class period to do the homework that I'm going to assign to you today. And we'll briefly talk about radiation because there really isn't much to talk about radiation. Okay, so we will finish 11.2 on Tuesday. And then on Thursday we will do 11.3 through 11.5. Or should I say, you will do 11.3 through 11.5. Okay? So that's the plan of attack so far. Okay, so let's talk about conduction. Okay, let's go. We are on page 364. Okay, where they give you Fourier's law. Fourier's law is one of the laws that we talked briefly when we did, I think, chapter 1. Came up, right? Fourier's law came up in one of the homeworks, I remember. Okay, so this is your equation where Q is the heat transfer rate. This is the heat transfer rate right here. Okay, L is the, if you had to guess huh? It'd be the thickness, right? Thickness of whatever you're going through. Delta T is the temperature difference between both sides, right? Okay, and then you have A, which would be area, right? Cross-sectional area, and K is nothing more than a constant. What's the name of this constant?
The value for it?
Thermal what?
Conductivity.
Conductivity. Thermal conductivity, and each material has a special, so it's material dependent. And did they give you that? Some of those?
They did not.
On the next page? Next page. Thermal conductivity of some materials at 300 degree Kelvin. So you have all these things, right? So let's look at what's high here. Looks like aluminum is pretty high.
Silver.
Copper is pretty high.
Gold.
Silver is high. Gold is fairly high. So why don't we use silver instead of copper?
Why?
Right? Who has enough money to put silver in there instead of copper, right? So that's why we'll use copper. Copper is cheap, and it is a very good, it has very high conductivity. Okay? So, you have thermal conductivity, blah, 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 material thickness, blah, 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 blah. Okay. Okay, so one thing we can do here is we have now we have a concept called thermal, not thermal conductivity, thermal resistance. Thermal resistance. So if we take this guy and you divide top and bottom by this, Ka, I can actually put this guy underneath here, right? Like that. And this guy is now called the thermal resistance. The reason why it's called the thermal resistance is because the higher this value, what happens to our heat transfer rate? It gets smaller, right? Okay, so for the same delta T, the higher this is, the less heat transfer you get. That's why, because that's why it's called the thermal resistance. It resists transferring the heat. Okay, that's why it's called thermal resistance here. Like brick. And so if you go over to page 367, it has that stuff, right?
Human fat layer?
Yeah, human fat. Ooh.
We should make our wires.
Paper does not do well with thermal conductivity.
I mean, nobody wants
Human
the
fat layer. Okay, that's no good. So that's good that it's low, right? It means that you are that much what? Resistance
More
to
resistant.
losing your body heat
Yeah.
when you're exposed to, cold weather, right?
Need more fat.
Okay, so let's flip the page, go to page 368. 368. Oh, so it gives you an analogy there, an analogy of how this equation is kind of like Ohm's law. And Ohm's law is this.
Isn't that the thing you say when
Meditating?
Oh.
Ohm's law, right? So can anybody tell me what the unit of this is? V,
Voltage?
velocity?
volts.
There we go.
R would be
Radius.
ohms resistance, and I would be, so we're talking about electricity here, right? What is I? I is
Current?
current. So it will be in amps.
Okay, it's not
Okay. You guys don't know this yet. Okay. We'll talk about this later. Okay. But there's something that's similar to this guy here, right? Delta T would be the difference in
temperature.
the temperature, right? So this voltage is a difference in voltage, right? From high to low, right? So if you think about it in your so this would be a battery, right? A DC battery going across a resistor, or sometimes actually you can build this correctly so that it actually lights up, right? You can build a lamp, you can, right, connect a battery to a lamp with the wires. You guys done this before. This is how a flashlight works, right? So you turn it on, right? So, again, the higher the resistance, the less heat transfer, the less amps current that is flowing through here, because you have that much more resistance here.
That's why high voltage have high heat, right?
So voltage, right? So if the larger the voltage, right, the higher the amps, right? The higher the amps. The larger the temperature difference, the larger the heat transfer rate. Same thing. So they're analogous to each other. Okay.
What if that whole shit hot?
Okay, so that's that. We talked about that. So if you go to page, bottom of page 368, they now give you a R prime. Okay, where this is R prime it's just R, but it's per area. So they're taking away the area. They're taking away the area part here, and they're going to say just L over K is R prime. It is R per square centimeters or square inches or something like that. Okay. Okay, so that's basically it. So I did not do any of the examples, and that is by design. Okay, that is by design. I want you guys to struggle through the examples as you're doing your homework.
I want you guys to have a hard time.
I want you guys to have
R factor?
Who wants us to fail?
no pain,
Okay.
no gain. Is that how that works? Or how does that work?
Yeah.
Lame.
I heard a lot already.
Huh?
I heard every day, but
I
I
said
don't seem to
already
be
heard
getting
a
any
lot.
better.
Doesn't seem to work for you?